So yeah, today's lecture is going to be on LCA and RMQ, which are topics that come up a lot in CP problems. So let's get started. So basically the idea in this lecture is we're going to go over two different ways to compute lowest common ancestor, LCA, on trees. One of them is a lot more annoying to implement and we don't usually use it, but it's nice as sort of an introduction to the idea of sparse tables and binary lifting, which are useful in other areas too. So using these two different ways to compute LCA, we're going to see a bunch of different ways you can use this topic. So okay, first, what is LCA? So the lowest common ancestor of two nodes in a tree is the node with minimal depth on the path between them. So like if you look at the path from 4 to 2, the highest node is 1, so that is the LCA of 4 and 2. If we look at LCA 6 and 7, the lowest node on that path is 3, so answer is 3. And for example, if we look at the path from 6 to 1, the highest node there is 1, so that would be the LCA. So given a tree rooted at vertex 1, say, we want to be able to do these queries very quickly. So we're going to talk about a way to do them in constant time and a way to do them in log n time. Both of them have n log n precomputation. But before we get into that, we're going to do a quick aside for RMQ, which stands for range minimum query. So basically for RMQ, you're given an array A of size n and queries of the form L to R, and you want to return the minimum value on the subarray from L to R inclusive. And we want this in constant time. So those of you who are here for our segment tree lecture will realize that you can do this with a segment tree also. However, this gives you log n time per query. And also, I think it's more complicated. Like I don't know, it's kind of close if you have like the really nice seg tree implementation. But this is definitely a lot easier to understand than the seg tree. The one big difference here is that we don't have updates. So we don't have to process any changes to the array. We just have to be able to do it for an arbitrary range quickly. So any questions so far? Okay. So yeah, again, if we have like a query like L equals 2, R equals 2, that's going to be just the one at position 2, so that's 6. L equals 0, R is 5 is the whole array, so the min is 1. And we want to be able to do this for any range. Okay, so here's what we're going to do for the precomputation. Let L be any value that's guaranteed to be bigger than log n. And by guaranteed, I mean like it's bigger than whatever your max log n can be. So in most cases, like with n less than or equal to 1,000,000, which is what you'll see in like basically every problem, you can use L equals 20 because 2 to the 20 is a little bit over 1,000,000. So that works. You just need 2 to the L to be strictly more than n. And you can also have it like dynamically, like you can have it be like ceiling of log n, but a lot of times it's easier to just work with a fixed value like 20. So you don't have to worry about like off by ones and stuff like that as much. So the complexity here is really like 20n and not n log n, but it's the same thing, it doesn't matter. So what we're going to do is define an array RMQ, which is n by L, where RMQij is the minimum value on the subarray of length 2 to the j that starts at position I, or up to the end of the array if that sort of overflows past the end. And this array, we call it a sparse table. So it's kind of a hard thing to visualize, so we're going to do a quick example for that right now. So let's say this was your array. This is what you would have in your sparse table. So let's look at it sort of row by row. So for the first row, again, what these rows represent is the minimum value on the subarray of length 2 to the j. So for j equals 0, that's the minimum value on the subarray of length 1 starting at that position. So that's just the element itself, right? Because at every position, subarray of size 1 is just the element. And the minimum value on that subarray is just the element. So the first row is just the array. Then the second row, j equals 1, now we're looking at subarrays of size 2. So for this first position, we're looking at 1, 5, minimum value is 1. For the next one, we're looking at 5, 3, minimum value is 3. And again, we go down to the end. The one thing to notice here is for the last one, there is no subarray size 2 that starts at 5, right? So we just sort of only go up to the end. You ignore everything that goes past the bounds of the array. So this is still 5. In the third row, we're looking at subarrays of size 4. So for example, in this I equals 1 position, we're looking at 5, 3, 2, 6, where the minimum value is 2. And again, we keep going. And then the same thing here for subarrays of size 8. So does the way this table works clear? We're basically getting the answers for every subarray that is a size power of 2.
So this is going to take n log n time to construct?
Right, so that's what we're going to get into now. So there's n log n elements here, right? But it's not immediately clear how to construct the table itself in n log n time. So for the first row, you can obviously get each of those in constant time because they're just elements of the array. But can you guys see how to construct the other elements in constant time?
I mean, you could start dynamically from the first row and just at each step to a greater j. Combine each subarray with sorry, and check each subarray with the subarray after to see which one has the lower minimum value, and then just combine those.
Right. Yeah. So we have the first row, right? So then we can do kind of like an induction type thing from there. So what you do is you have this subarray size 2 to the j, starting at position I, and we want to split it up into 2 subarrays of size 2 to the j minus 1, right? So like, let's say you're on the first in j equals 1 row. You want to find the min on the subarray size 2, so we split that into 2 subarrays of size 1, which we have pre-computed in the previous row. And notice that the first subarray of size 2 to the j minus 1 is going to be directly above you, right? Because starting at the same position. And the second one is going to be 2 to the j minus 1 ahead of that. So like here, we want size 8 from here. So we do the size 4 from here, and then we jump forward by 4 to get this one. And one edge case is if jumping forward by 2 to the j minus 1 takes you out of the array, then we just ignore it because we don't care. We're past the end. So in this way, we can get every other element as the min of at most 2 other elements in the row above it. Does this make sense to everybody? All right.
Yeah.
Cool. So the code for this would look something like this. So we have this RMQ array that stores the sparse table. For the first row, we just set it equal to AI. And then for every other row, we do what we just talked about, which is, again, you take the element directly above you, which you know always exists. And then you see if the other index is valid. So if that's less than n, then you take the min of that with your second element in the row above you. So this is basically just doing what we said before. Okay, so this gives you the setup. So basically, we have the answer for all subarrays with sizes that are a power of 2. So now, how can we use this to efficiently do queries for arbitrary subarrays? And you guys can give any solutions here. So like, eventually we're going to get down to a constant time solution. But if you guys have like a log n solution, for example, feel free to share that.
Yeah, we could do log n by like finding the biggest power of 2 that's like less than or equal to the length of the subarray you're checking.
Yeah.
And then like check the min for that in the table, and then basically subtract, like you can increase the index you're on and then decrease the length by whatever the length is you just checked.
Yeah, exactly. So the log n solution looks like this. And this is, again, kind of like what you would do with this egg tree, is sort of break it up into these disjoint regions, like at most log n of them. And yeah, like Ryan said, what you do is you basically keep pulling out the biggest power of 2 until you're done. And that's guaranteed to terminate into most log n steps, because you're basically looking at like the binary representation of your size, right? Because like 7 would be 1, 1, 1 in binary. So you have like your size 1, your size 2, your size 4. The same thing with size 5, that you have 2 to the 0 plus 2 to the 2. So you have your 1 and your 4 here. So yeah, if you break it up like this, keep greedily pulling out the biggest power of 2 you can, that gives you log n query time. So now the question is, how do we improve this to be constant per query?
Does pre-computing count?
What do you mean? So we have the
pre-computing.
pre-computation.
Oh, so we've already pre-computed the table.
Yeah, oh yeah, we have the table. Yeah, so this is all once we have the table. Because like once we have the table, this getting the answer for this is constant time, and this is constant time, and this is constant. So you have your log n chunks, each one is constant, and then you get log n queries in total. But yeah, this is all after pre-computation.
I mean, pre-computation is n log n though, right?
Yes, yeah, the pre-computation is n log n. But now we want to be able to do queries constant time.
Can you you take the biggest power of 2 that is smaller than like b minus a, and you compare it from the start and then from the end, kind of, if that makes sense?
Yeah, that's exactly what we do. So the key here is we don't actually need these subarrays to be disjoint. So what we can do is take the biggest power of 2 that fits inside there, and take the leftmost that many and the rightmost of that many. And that's guaranteed to cover your whole range, because if it didn't, then 2 times that would fit inside, and then that's not your biggest power of 2 anymore. So we know that this is guaranteed to cover your whole range. And again, we don't care about overlap, because the min stays the same no matter how many times you include each element. So we can include each element twice and it's fine. So yeah, again, for an example, like if you have 7, you could take like these 4 and these 4, and take the min of those 2, and that would give you the answer. And same thing for the 5. Right? Okay. So then the code for that would look basically like this. So the sort of tricky part is getting the biggest power of 2 that fits inside. And most languages have some kind of built-in function that does this. And I mean, it's not like really constant time, but it's optimized so much that it's basically constant time. So like built-in CLZ for C++, which counts the number of leading zeros in your int, or like integer.highest 1 bit in Java. So these are all basically constant time. So we can say that the queries are basically constant time. And yeah, for C++, if you're using ints, you want to use 31 minus this. If you're using long longs, you have double the number of bits. So you want to do 63 minus this instead. And note that you have the LL suffix here. So yeah, this will give you your range min queries in constant time now. So before we move back on to LCA, anyone have questions on RMQ? Okay.
I have a question.
Yep.
Could you do this for things besides the minimum, or is it pretty much only minimum and maximum?
So yeah, so the one thing that has to work is it has to not matter if you count something twice. So like if you were doing sum or something like that, then that would matter because now you're adding this element twice. So if you do the log n solution, then this works for basically anything that would work for a seg tree. As long as it's like associative, basically, is all you need. But for this, trying to think of what other functions would work for this. GCD, I think, would work. Yeah, anything that it doesn't matter how many times you add each element would work with this. But that does kind of limit you a lot more than the things you can do this way. Okay, anything else? Okay, so now we're going to get back into LCA algorithms. So the first one actually uses RMQ. So what we're going to do is you have your tree, then we're going to do a DFS and store every vertex you see, including repeats, in a list, say A. So like if you have this tree, you'd go 1 to 2 to 4 to 2 to 5 to 2 to 1 to 3 back to 1. And notice that we're traversing every edge exactly twice. So our total number of steps is 2 times, or our total number of elements in the array is 2 times number of edges plus 1, because sort of every element in the array except for the first one corresponds to moving down or up an edge. And then you have also the first element. Okay, so yeah, so your list is of size O of n. So we can basically just assume that this is like, we can basically do any like n log n or whatever on this that we want now. Okay, so now what we're going to do is we're going to make another list of the depths of the elements in the first list. And you can sort of do this in the same DFS, right? Because when you DFS down to the child, you can sort of pass it depth plus 1. So like in this tree, we would have 1 at depth 0, 2 and 3 at depth 1, 4 and 5 at depth 2. So if we look at D, that would look something like this, because you go like 0, 1, 2, 1, 2, 1, 0, 1, 0. And then the third array we're going to store is IDX, which just gives you one occurrence of I in the first list. So for example, IDX of 1, 1 appears at position 0 here. So we can make IDX of 1, 0. 3 appears at position 7 in this list. So we're going to make IDX of 3, 7. So basically all this is doing is we want to be able to find an arbitrary occurrence of every node in constant time, basically. So like we want to be able to like find a 3 and find a 5, right? Or something like that. Okay, everyone good with the arrays and the pre-computation we have so far?
Sorry, could you repeat what IDX is?
Right, yeah, so for every node in the tree, we want to know one index of that node in A. So like, let's say node 2. That appears at position 1 here. So we can let IDX of 2 be 1. So this is 1 index here. So this 0 is IDX of 1. And this is IDX of 2, IDX of 3, 4, 5. Right, because we have like 5 appearing at position 4 and 4 appearing at position 2. And it doesn't matter which one we pick, right? So we could just as well have let IDX of 1 be like 6 or 8. But yeah, we just want any arbitrary one, basically.
All right, thanks.
Okay. So now what we're going to do is do RMQ precomputation on D, so our array of depths. And we also need to keep track of the index of the minimum here. So what you can do is store the min as like a pair of min comma index. And then if you do like the normal min, at least in C++, that'll give you the index of the min. Actually, it doesn't matter which index we take. All we care about is, again, it's kind of like the IDX array. All we care about is one index that contains a minimum value. This is confusing that I called this IDX2, but this is a separate IDX. This is the index of the minimum within the subarray. Okay, so now we have this RMQ precomputation on D. So if we're looking at any range, like let's say we're looking like on this subarray, we can find the minimum depth in constant time. So here it would be 0. And what we're claiming now is if you want the LCA of two nodes, take IDX-A and IDX-B and look at the minimum depth in between them. So for example, if we have, let's say like 3 and 5. So IDX of 5 is 4, IDX of 3 is 7. So we're looking on this subarray, and we sort of shift that down. So now we're looking at that subarray on D. We get the minimum value here, which is at this index. And now we shift back up to get what node that corresponds to, which is node 1, which is indeed our LCA. So we're going to do a sort of quick justification for that. So yeah, so any subsegment between IDX-A and IDX-B represents a path potentially with repeated edges between A and B. So again, we have the same A array here, right? Let's let A equal 4, B equal 3. If we go from IDX-A to IDX-B, there's only one choice for each. So that subsegment is 4, 2, 5, 2, 1, 3. And if you look at that, 4, 2, 5, 2, 1, 3, that's a path in the tree with repeated nodes and edges, but it's still a path. And note that any path between them has to go through the LCA because otherwise 4 would be kind of stuck in this subarray down here, 3 would be stuck in this subarray. And the LCA is actually the minimum depth thing that can be on this path, because if you go past the LCA, like let's say we had another edge up here, and let's say our path was like 4, 2, 1, I don't know, 7, 1, 3 or something. We can't have that ordering happen with the DFS, because the way the DFS works is you go down an edge and then later you go back up. There's never a point where you go up an edge and then you go back down. So if we had something above here that we were going to, like we went 4, 2, 1, 7, 1, 3, we would be going up this edge and then down it later, which can never happen. So then we know that the minimum depth vertex on this path has to be 1, or the LCA. And that's why we can use this RMQ on the depths to find that vertex. Yeah. So does that argument make sense? It can be a bit confusing.
I mean, I think it makes sense actually. Like when I first saw it, I was thinking that you were enumerating, you're ensuring that the parents of a node have a smaller index, and then I thought you would actually just find the minimum on the initial array rather than depths. But yeah, I guess that requires some extra pre-computation. Also, I don't know if what I was thinking even works.
Yeah, I just happened to draw this tree like that. But that is basically what you're doing with the depths, is you're sort of assigning them all a number based on their level. So that works.
So that's obviously a much easier way than to come up with your own sorting of it.
Yeah. Okay.
Wait, wouldn't that just be breadth first search though? To get to assign the nodes like the way that Andrew was describing, wouldn't that just be breadth first search?
Yeah, BFS or DFS would both work.
Okay.
Because it basically does the same thing in a tree. So yeah.
This is for this works for any tree, right? It's not just limited to binary trees.
Yes, any tree. Yeah. So everything we're going to do with LCA is with general trees. Okay. Anything else? All right, so this is the LCA method that we don't really use because you have to implement the RMQ and then you have to do like the depth thing and have your 2 arrays and everything. And it's just a lot more complicated than the way we're going to go over now. But it's a nice application of the RMQ thing. And also, if you have to do your queries in constant time, like if you have some really restrictive time limit, this does save you a log-n factor from the other way. But yeah, so now we're going to go into the nicer way of doing it, which is binary lifting. So we're going to make a different sparse table this time, same dimensions, n by l. So l is the same thing as it was for RMQ. Except here, we're going to have para ij be the 2 to the jth parent of I. So for example, para I0 is just the direct parent of I. So it's like the normal parent of I in the tree. And again, here we have to be careful about overflow, but this works out much nicer than RMQ because if the 2 to the jth parent goes above the root, we can just set it equal to the root. So like, let's say we want like the 8th parent of the root. We can just say that that's the root. And this turns out to simplify a lot of our code going forward. So again, we have this sparse table. So the bottom row is always going to be all ones, because if you do like say the 2 to the 19th parent of every vertex, that's always going to get you like past the root. So that's always going to get you to 1. And once again, the first row is easy to compute because that's just the parent of I, which we can compute in the DFS. So like parent of 3 is 2, parent of 6 is, I should say 4. But now the question is, how do we compute the other ones in constant time? And the hint is it's very similar to what we did in the last table. So yeah, again, like this second row here represents the 2 to the first parent. So like the second parent of 5 would be 2 because you go up twice. Second parent of 7 is 3. And then here is the 4th parent. And no matter what node you start in, if you go up 4 times, you hit 1. So
I don't know if this is like the same way as that, but I was thinking like you go through DFS basically log n times, and you start like at the top, and then at each node you just like add its like 2 to the jth parent, like 2 to the j minus 1th parent that you already pre-computed in your previous run of DFS, I guess.
okay. Yeah, I think you're on the right track. Yeah, and I think that's actually like closer to how I implemented in the code than what we're going to talk about. But like, how do you compute that given the stuff you already have?
Could you like if you look at I equals 5, for j equals 0, it's 3. And then for j equals 1, you look at what the value of I equals 3 at 0 is, and it's 2. So
right, yeah.
Okay.
Yeah, exactly. So what you want to do is you want to go up by 2 to the j minus 1, and then go up by another 2 to the j minus 1. So what that looks like is, yeah, so the 2 to the jth parent of I is the same as the 2 to the j minus 1th parent of the 2 to the j minus 1th parent of I. So basically what you do is, let's say we're looking at the 4th parent of 7. So we get the 2nd parent of 7, just 3. And now we want the 2nd parent of 3. So we go over to the 3 column and we get 1. So it's sort of the same idea we had in the other one, where you break it up into the 2 smaller powers of 2. And then you only have to look at 2 elements in the row above you. And this is where the overflowing to 1 thing is really nice, because there's no need to handle an overflow case here. Because if you hit 1, then everything every jump you can do from there is just 1. So this sort of naturally handles the overflow case by itself, which is nice. All right, does this make sense? Cool. So, yeah, so the code for this, for pre-computing this, here's one way to do it, where you sort of do it all within a DFS. So you assign I, the depth of I to be the depth of P plus 1. And then the parent I0 is, again, just the direct parent, which we can pass in as a parameter to the DFS. Note that when we call it on the root, we want to make the parent of the root itself so that we get all this nice overflow handling done. And then you can also do this outside once you've finished the DFS, but it fits just as well in here because we've already computed everything for all the ancestors of I, right? So as we're computing para IL for every L, we've already computed it for all the ancestors, so we can use all of those. So again, this is more like what Andrew was talking about, where like you sort of do it in the DFS after computing it for the ancestors. But you could also just do it in a similar way to how we did RMQ, like have like a nested for loop in main or something.
Well, I wanted to do it with DFS like a bunch of times, but there's absolutely no point to doing that.
Oh, okay. I mean, I think you could adapt this to do like a DFS for every L, and I think that would work. But it'd probably be more code, but I'm pretty sure that would work. Yeah, and then you'd basically just DFS from all of the children of I. So basically everything adjacent to it that's not the parent. Oh, oops. Okay. And the reason we have this depth array is that we're going to need this for the queries. So we're not like explicitly using it here, but we're going to need it for queries. Okay. So step 1 of the queries is, let's say we're trying to calculate LCA of A and B. The first thing we want to do is get them to the same depth, right? Because if they're not at the same depth, we can sort of reduce the problem to one where they are at the same depth. So like, assume without loss of generality that depth A is greater than or equal to depth B. What we do is we set A equal to its depth A minus depth B parent, which will bring it up to the same level as B, basically, right? So do you have a picture of the tree over here? Yeah, so like let's say we have 7 and 4. Basically, the idea is we want to move 7 up to 3 because now they're at the same depth. And note that we can get like the kth parent for any k in O log n because we can greedily take the largest power of 2 that sort of fits inside k until we're done. So like if we need the 5th parent, we can take the 4th parent and the 1st parent. And it's sort of that idea again. Okay, so now after doing this, which takes log n, we have A and B at the same depth. And if they're the same vertex, then we're done, because that means that that vertex has to be their LCA. Because that means we had a case like, for example, 2, 7. So if we move 7 up to the same depth as 2, then they're equal now, and that's the LCA. So that's what happens when one vertex is like a child of the other, or a descendant of the other. So now we just need to handle the case where they're not equal and they have the same depth. And so the idea with this is sort of, we want to move them up together as far as we can, such that they're not equal. So if we let A be the difference in depth between like A and their LCA, right? We want to set them equal to their x minus first parents. And again, we can do this in log n by just pulling out the biggest power of 2 over and over again. Because again, like if we have 5, we break it up into 4 and 1, and it's that trick again, except now, instead of just moving up A, we're moving up A and we're moving up B. And again, we only do this when moving them up does not set them equal to the same parent, to the same vertex. Because if we move them up to the same vertex, then that means we are like at or past the LCA. And there's no way of telling if we're past the LCA or if we're there. So we want to stay in a range where they're not equal, so we know we're strictly below the LCA. So now we've found the highest vertices that are strictly below the LCA, right? So now we just take the first parent of one of those to get the LCA. So questions on this? Because this is also kind of abstract.
By the way, like, weren't we searching for constant time? Isn't this like not, sorry, yeah, constant time per query? Isn't this like log n-ish? I
Right,
guess it's
yeah.
log n.
No, so this is log n. And yeah, so in general, LCA queries with this method are in log n, but usually that doesn't matter. So
Actually,
yeah.
sorry, what about like for the previous method? Isn't it also log n because you have to find the largest power of 2?
Right. I mean, we kind of hand wave that away by saying like there's built-in instructions that do that with like a very good constant factor.
I see.
So it's like, I mean, technically it's log n, but it's like those instructions are so fast that they might as well be constant time.
Wait, actually, wouldn't it be log n because you're like finding the power of 2 under it, and so like there's only log n powers of 2, and then you can like binary search on the power of 2 to be like log n or something.
Well, you'd have to repeat that log n times because the distance might not be a power of 2, right? It might be like any number. So what you can do is like just break that up into powers of 2, into log n of those. And then each of those will be constant time. Yeah, because you can't always do it in like one power of 2 check, basically. So what we're doing here is we're not moving them up by the biggest power of 2 that keeps them below the LCA. It's moving them up by the biggest number that keeps them below the LCA. So here,
I get it, yeah.
Okay, yeah. So like if we have 5 and 6, we want to move them up to 3 and 4. Is basically what we're doing here. And then once we have them at 3 and 4, we just take the parent of say 3, and that gives us the answer. Okay. So the code for this would look like this. So this part is basically doing step 1 that we were talking about. So first we want to make sure that the depth of A is at least the depth of B. So if it's less, we can just swap them. Because it's symmetric, it doesn't matter. And then here, what we're doing is we are sort of greedily pulling out the biggest power of 2 of depth A minus depth B. So this is basically saying if depth A minus depth B is at least 2 to the L, then we set A equal to its Lth parent. And then at this point, once we're done with this loop, we know that depth A equals depth B. So then if they're equal, we can just return A. Otherwise, we do sort of a similar thing to what we did here, and we go through powers of 2 descending again from L minus 1. And if their Lth parents are not the same, we can move them up, and that brings us closer to the LCA without touching it. And then at the bottom here, we just take the 2 to the 0th parents, the first parent of A, which gives us the LCA. Okay, questions on this? Cool. All right, so we can get into problems now. So the first problem is distance queries. So you're given a tree and you want to answer queries of the form distance between U and V in terms of number of edges in log n time. And assume we have all the LCA pre-computation done. And I mean, I guess assume that we did it the second way, because that's the way we would do it in a contest usually, because it's just easier to code. So yeah, for example, like between 4 and 3 is 3 edges. Yeah, oh crap.
Isn't this just difference in height between like the first node and its first common ancestor plus the difference in height between the second node and its common ancestor?
Yeah, exactly. So the number of edges between A and the LCA is depth A minus depth C, right? So like here, depth A would be 3, depth C would be 1. So if you subtract them, you get 2, and we have 2 edges here, right? And then we do a similar thing for B. So depth B minus depth C is 1. And then that covers all the edges on the path. So the distance is just the sum of these two values. And you can sort of simplify that to depth A plus depth B minus 2 times depth C. And this is a thing that comes up a lot in LCA problems. Okay. So the second problem, okay, kth vertex. So now if you're given a tree on n vertices, we want the kth vertex on the path from U to V. Again, log n time. And again, we have all the pre-computation done in advance. So like if we're looking at the path from 4 to 3, that would consist of the vertices 4, 2, 1, 3 in that order. And we want to be able to do each of these queries in log time.
This is somewhat messy, but like, so you calculate the common ancestor, and if the difference in, if k is less than the difference in depth between the first node and the common ancestor, then you just calculate the kth parent by using like O of log n steps. And otherwise you calculate the, like, I guess the total, the number of edges minus k from 3, from the second node.
Yeah, exactly. So the idea is we can kind of split it up into 2 cases. So first we can detect if the vertex lies on the path from A to the LCA. And yeah, like you were saying, we can do that by checking if depth of A minus k minus 1 is at least depth of C, which is the LCA. So then we just take the k minus 1th parent of A, which again we get in log n by breaking it up to powers of 2. Otherwise, it's going to be on the descending side of the path. So we can use the previous problem to get the total number of edges, and then sort of subtract off k from that, and go up by that much. And again, we do that by, oh god, keeps going forward. And again, we do that by breaking up into powers of 2. All right, questions on this? Basically just splitting it up into which half of the path does this vertex lie on. Okay. So now you're given an n by m maze where you're guaranteed that there is one path between any pair of squares. And you're also given a bunch of checkpoints within the maze. And you want the minimum length of a path that visits all the checkpoints in order. So like you go from 1 to 2 to 3 to 4 and so on until the end. And you can start and end anywhere. This was actually in a recent contest we did. And we want an nm log nm solution, where nm is the total number of squares you have here.
So this is just like not actually a solution, but like you would always start on the first checkpoint, right?
Yes, yeah, you always start on the first one and end on the last one.
Can we like sort of arbitrarily pick a like the first checkpoint and then sort of go through the maze and connect it to I guess all of the nodes you find in like a tree. So the ones you connect to is like a child of it, and then sort of when you go on from that one through the rest of the maze, you are like adding sort of the nodes onto that one. And then that was probably a bad way of explaining it, but
So
then you can just Actually, I forget what I'm going with this.
I think you might be on the right track.
Yeah. I had something, but like I just
I
forgot.
was kind of thinking about the same thing, but I think there like might be cycles, so I'm not sure how to prove that it's a tree.
So you're guaranteed that there's exactly one path between any pair.
Oh, oops.
Yeah, so you don't have any cycles.
So then that solution kind of works. You start at 1, and you generate a tree for every square on the maze, and then you like calculate the distance between like any point and any other point just by calculating the sum of the edge distance from them.
Yeah, exactly. So this just reduces back to the first problem. Because if we represent this as a tree, you can root it anywhere. Then all we need is like number of edges on the path between every 2 adjacent checkpoints. So like, for example, the path from here to here would use 7 edges. So that's like 8 squares, right? And then you basically just add that up for all of your adjacent checkpoints. And the one thing is you just have to be careful about like double counting squares and stuff like that. So you probably have to like subtract off k at the end or something. But yeah, this just reduces to k queries where you're given 2 points, say 1 and 2, and you find distance between them in the tree. And you do that for every pair of checkpoints that are next to each other. So yeah, that basically solves that one. And then our last problem is dynamically rooted tree. So for this one, you have a tree and vertices initially rooted at 1, and then you have 2 types of queries. So 1 is you set the root of the tree to be v, and 2 is return the size of the subtree of v with respect to the current root, right? So when you change the root, you're also changing like what the subtrees are of everything else. So we want the size of the subtree of v with respect to the current root. And we want these queries done in log n or better.
Do we have more than log in time in the beginning to pre-commute stuff?
Yeah.
Okay.
So you can do n log n pre-computation, but you can't like redo that every time you get a query because yeah. But yeah, at the beginning you have n log n. Yeah, that kind of leads into a hint that you can't like redo pre-computation every time you change the root. So is there a way to do it where you don't actually change the root for the pre-computation? Yeah, so a few hints in general for this one. Let's keep the actual root fixed at 1. And have some variable r that holds like your current root. Okay, so now, and initially we can like do a DFS to get sizes of subtrees with respect to 1. So now our queries are very easy. All we have to do is set R equals V. And we can sort of split up S queries into 3 subcases. So if V equals R, then the answer is obviously going to be N, because the subtree is just the whole tree, because the size of the subtree of the root is just N. And then we also want to check if V is in the subtree of R with respect to root 1, because again, we're not going to do any other computations. And we can check this by checking if the LCA of V and R is R. And then the other case is V is not in the subtree of R. So how would we answer the queries in cases 2 and 3? So case 3 is probably going to be easier to figure out.
That would just be if the LCA of V and R is not equal to R, right?
Right, yeah. So case 3 is just we're not in either of the first 2 cases. Yeah, so it's just LCA V and R does not equal R.
The second case just like the same as it would be with the same root? Or am I like not visualizing this correctly?
For case 2 or case 3?
No, it feels like case 2, and I'm like kind of confused about case 3, but it feels like both case 2 and case 3. I don't know.
Yeah, you're close. So it actually is the case for case 3. So if V is not in the subtree of R, then the answer is, wait, did I get this backwards? So if V is here, yes, I have this backwards. So this is if R is in the subtree of V.
I was thinking more for case 2, and for case 3, I was like kind of trying to visualize it, and I wasn't so sure about it. But yeah.
Yeah, so this should all be R is in the subtree of V. Yeah, that's my bad. So okay, in this, this is V now. Yeah, this should not be R. If any of these vertices are R, then the size of the subtree of V stays the same, right? Because like if you imagine moving any of these red vertices to the top, the size of this subtree stays the same, because you're sort of not changing anything internally here. You're just shifting these around. So yeah, so if R, yeah, so if V is not in the subtree of R, no, if R is not in the subtree of V, sorry, then the answer is size of V. Yeah, so now the other case is if the vertex is rooted, say, somewhere down here, how do we calculate that?
Can you, wouldn't that just be like N minus the size of the, like the edge going down into where V is? Did that make sense?
Yeah, exactly. So what you want to do is, yeah, so, oh, I think I got it right here. Yeah, so if R is in the subtree of V, we want to find the child of V whose subtree contains R. Right, so you want to look at the edge going out of V that is on the path to R, basically. And then if you let this one be U, then the answer is going to be just N minus size U. Because if you imagine rotating R up to here and reorganizing the tree to like fit that, everything except for this subtree here is going to fall under V. So we just need to subtract the size of this subtree out from N. And the way we compute U is that this is just going to be the depth R minus depth V minus 1th parent of R, which again, we can compute in log N by breaking it up into blocks. So yeah, we find that vertex that way, and then we just subtract that out from N. Right, so questions on this? And I know this is confusing, especially because I kept getting R and V backwards, but any questions? All right, cool. So thank you guys for coming. We have a bunch of stuff in the next 2 slides, which are on the Discord info channel. You guys want to check that out? We have CP algorithms, links for LCA, template, and some problems we did just now, as well as a couple other problems. You guys want to check those out. So yeah, thank you guys for coming, and hope to see you guys next week. All right.
Thanks, Joe.
Thank you.
Yeah.
See you guys.
Bye.